All right, well, welcome to another exciting episode here at Spain Park High School of Advanced Level Chemistry. Today is Thursday, March the 17th, St. Patty's Day. I don't have any green on because we have a tennis match today, so I had to wear Spain Park colors. Okay? Now, listen. We're talking about states of matter. Oh, and by the way, any of you watching this that are enjoying these exciting chemistry episodes, please feel free to subscribe to my channel. All right. So,
only 10% of you that watch are subscribed.
That means only one person subscribed. I think I have 80 viewers. And so, okay. So, listen, we're talking about states of matter. How far did we get in these notes on?
7.
Seven.
I don't think we finished capillary action.
Okay. So, we're going to go and we're going to take a little bit of a Back to the Future. Okay? We were talking about surface tension. What is surface tension?
It's tension on the surface.
Caused by uneven attractions on molecules.
It pulls down and not up because
Okay. So again, I have a paper clip sitting here on the bottom because I put it in the two identical paper clips, but if I put it in flat and get it just right on the surface, I have it floating on the surface. So it's not because it's less dense it's floating, because here's one down at the bottom proving that it's not less dense. Okay? But we have one on top. It's got that skin, that uneven surface tension. But what causes that surface tension? Again, so here's my beaker of water.
Uneven, like, pull on it.
So this water molecule down here is getting pulled in every direction by the other water molecules around it. Okay? All the water molecules that are wetting this water molecule are touching this one and pulling it in all the directions. But the water molecule that's up here on the surface, okay, which way are they getting pulled?
Down and to the right.
Down to the side, this way, this way, this way, this way, and this way. So it's an uneven pull. Okay? So it's the cohesive forces. And in water, what are those cohesive forces? Hydrogen bond's the strongest, the most definitive one. But what else? LDFs. Dipole, dipole. Okay? We say di because di means two poles. Okay? Okay? So, it's those attractive forces. So now on your table, yesterday meaning the last time we met, yesterday we did water on a penny and we tried to see how many drops of water we could do on a penny. Okay? Now we have one set up per table. Okay? And I need to give you your water back. Okay? Now, in one beaker you have water, but in another beaker,
Don't sip it, guys.
yeah, do not drink the alcohol.
Dude, that smells like.
Okay? But listen, I want to have a competition. You should have 2 pennies. I want to see how many drops of water you can put on the penny, and then on the other penny, how many drops of alcohol you can put on the penny. You can tell by smell. Okay, they're supposed to be the one on the left. Yeah, go ahead and start. Y'all join together. You out of water? That's darn boys. Water in it originally.
This penny seems so stuff.
It's had a life, huh? I don't know if this is one of dolls.
Ashley, can you move it to your right?
Is that yours?
Alcohol doesn't make them know when you
I'm scared to touch this stuff though.
You don't have to be scared to touch it, just don't lick your fingers.
No, it's gonna burn my skin off.
It is not gonna burn your skin off.
Like, oh my god.
I have a cut on my finger. If I put my finger in the.
Yeah, now that'll hurt.
You didn't even dry it off. You okay?
Is it burning?
Yo, me too.
It helps nausea.
Future alcoholics in America.
Like gas, that stuff smells so good.
Dude, I can.
Yeah,
You're supposed to be dropping the drop onto it. You're just kind of smashing it in
I need a
there.
fresh tank.
I'm picking it back up.
Yeah.
You didn't put his paper towel, just dry it. Well, you got one right there. Just dry it.
That was like so straight.
All right, what are we getting? How much?
20 with alcohol.
40 without.
40 with
We
alcohol?
also have the small ones, so like the drops.
Okay, well now use that same one to do water. Use the same dropper to do water.
You want us to like wash it?
Okay, I don't know how many
You could
drops I
just
did.
squid some water up and then squirt it on the table and then
Alright.
It'll get the
Let me
table.
get a paper towel.
here, I'll get you some water.
I stopped counting after 50 yards.
Is that for us?
Yeah, just use the same dropper. Just squirt water up into it and then squirt it on the table.
Is 40 with alcohol good?
Now it's clean, now it's water.
40 with alcohol, how much will that max?
Well, that's pretty high for alcohol. Most of them are in the 25 to 30.
Well, I promised
Oh
to
my
not
gosh.
Okay, so let's just see now with that small one.
They got like, yesterday they like.
I did notice
Something and we only
Yeah.
got like.
alcohol expanded a lot.
Get the camera on now?
Yeah.
No, because then I had to have all the video
Just
stuff.
hold it like this.
Oh, I just made it.
Yeah.
Somehow managed to put 8%.
Okay, so, hey, give me some results here.
20 drops of alcohol.
27.
27 alcohol.
32 water.
32, that's garbage.
Really, that's the only difference, 27,
Or I
32?
got 20 alcohol, but then Luke was like doing tiny, like.
Okay. Well, we need some more definitive data here.
Well, yeah, we got like 60 over here on the wall.
60 of water.
I don't know.
You guys
how much
like
did you get?
And 828
Not having-
of alcohol.
Okay, that's a little bit more realistic. 60 of water, 28 of alcohol. Somebody, well, they theoretically got to 136.
I don't
Set a new
believe that.
Guinness Book.
139.
Guinness Book of Records for drops. Okay, but I'm not sure it was verified. The official drop.
She's on 47 of alcohol.
Yeah, the official drop police. I don't know if we have official drops going in on
Yeah, I
that.
don't believe
It might
that.
have just been taps with them.
It was
Water
definitely
just now?
tabs.
Okay, now,
One drop.
what is she doing? Water or alcohol?
Alcohol.
Okay, do we have here, pass you your alcohol one right here. Which one's your alcohol? Okay, now listen, use the same dropper, just squirt some out, squirt that out, and then suck some alcohol up into that
That's
dropper,
really not even a drop.
and now just squirt it on the table. Just squirt it onto the, not on the penny, just on the table somewhere.
Cause it don't.
The whole thing.
You feel like you are.
Okay, because now you got all the water out. Okay, so now you're just pure alcohol.
Yeah.
It does spread, okay, that's the whole point that I'm trying to make here. Go ahead, just drop it. Okay, and dry all that off, dry the whole penny.
63 with alcohol.
63 and 120 something with,
139.
139 with water, 60 something. So in real person's terms, that's 60 with water and 30 something with alcohol.
I think we should have done by the weight, not by the
She
Are we
did.
doing, all right, are we doing Fight Club, putting stuff on your cuts, you know, on purpose? Okay, sit down, baby. No, it's alcohol.
We got 98.
I was gonna use acetone, but we didn't have enough.
We got 98 with water.
Alcohol 98.
Okay, so wait, here we go. They used the exact same dropper. They didn't use two different drops. Listen, they used the exact same dropper. How many with alcohol?
40.
40, how many with water?
98.
98. So significantly more with water. You guys over here had what with what?
It was 41 water and like 26
41 with water, 26 with alcohol. What did you guys get in the back?
We had
32
with
water.
and then 20 with alcohol.
Okay, 32 with water. Okay? Are they officially doing it back there now?
Yes.
Okay, they're
I
trying to
think we're the winners for
trying to
that.
verify
I think I
the result. Okay, he just cleaned it, He rinsed it with just the new liquid. Okay, now while they're validating their data, here's alcohol, here's water. Okay? Okay, Luke? Put it away. Put them away. I'm tired of fighting. Okay? Now listen, let's get to what we're trying to get to on this. Okay? Surface tension is caused by the cohesive attraction creates a skin. Okay?
Uneven. We put uneven the other day.
Or, okay, uneven. We'll go with uneven. Uneven attractions. Okay? Cohesive forces are attractions between like molecules and attractive forces between unlike molecules. Okay? And then how did water get from the roots?
Capillary action.
Capillary, not caterpillar.
Caterpillar action.
Okay? Now, alright, come on, y'all.
I got 63 for alcohol.
Wow. Versus how much with water? Okay, so you guys are on the same math as they are, so.
Yeah, there you go.
Alright, but the whole point is this, okay? Is that the surface tension here is caused by these attractions between the molecules. Okay? What can we say then? Does alcohol have higher or lower surface tension? It's got less surface tension. Okay, alcohol's got, so what does that mean about its attractive forces?
They're not as strong.
They're not as strong. Okay, so there's not being pulled together as tightly. And so therefore it can't form the dome gives way faster. They're not held together as tightly because yes, it has hydrogen bonding right here. But we have all this non-polar part here that only has the London forces. It's not nearly as polar as water, which has the two H's. Water is very polar. It's got two places for hydrogen bonds to form. Its attractive forces, its cohesive forces, its IMFs are very strong. As a result, it has very high surface tension. And so detergents use what's called surfactants. Okay? Now, I have this piece, it's called cheesecloth. It's just kind of, you can just see the pores in it, okay? So, okay? If I put this over the top of this beaker, seal it down, okay? Now I turn this beaker that has water, it has water in it, okay, just to verify. It's got water in it, okay? So I turn it upside down. Even though it's got pores and holes in it, the water really doesn't come out.
Yeah.
Why not?
Is it because the water on the bottom is like sucking it up?
The water on the
No,
bottom.
like, so you see like the water that's like closest to your head is like pulling.
There is no, the water level's right there.
It's the surface
tension and the air pressure.
Okay? The surface tension of the water molecules is forming a seal across the little tiny pores and not letting the water out, even though there are pores. Now I can just do this and the water can come out, okay? If I let some air in. But it's the pores there. So what happens when you have laundry detergent, it's a surfactant, it lowers this surface tension. and causes the molecules not to be held as together as tightly. So then the dirt doesn't get trapped in the pores of your clothes like this is getting trapped. The water doesn't really get through. It allows that to open up and allows the dirt to be able to get through. So that's what laundry detergent does, is it lowers the surface tension. A good ACT word is surfactant, okay? It lowers surface tension, okay? So the strength of the surface tension is dependent upon the strength of the attractive forces. The stronger the attractive forces, the greater the surface tension, okay? So if you were to go, here's some mercury. Okay, come over here. Here's some mercury. Notice how the beaker on the inside, water wets, it's attractive, it's got adhesive forces as well. It attracts and sticks to the glass, so you can tell the glass stays wet. Okay, but mercury inside of this, if you look at this glass, is the mercury sticking to the glass at all?
No.
It's a dry liquid. Unlike water, not all liquids are wet. Okay? This one has such strong cohesive forces. It's narcissistic. It's much more attracted to itself than it is to anything else. And so as a result, it doesn't stick to the glass. As a matter of fact, when you want to go and you have the meniscus in water, okay, so when I go and I fill up this graduated cylinder, we get this curve. I'll be over here. We get this curve up here. Why do we have the meniscus? LG, you just cannot. No, you can wait until much later to throw that away. It's not like it's going to blow up or something.
Hey, you got your extra.
Okay?
You gotta stand 2 minutes.
Okay? So, we have the meniscus. It's because the water is attracted, has adhesive forces to the glass. You can see up here, the water is all stuck to the glass up here. It's got adhesive forces crawling up, but then it's got the cohesive forces pulling it together. A sphere has the least amount of surface area. So it kind of curls this way. Well, if you fill this with mercury, mercury has zero attraction to the glass. Only an attraction to itself. It's got a reverse meniscus. It's going to have the dome. Because it, again, is attracting to itself, so it's not attracted to the sides at all, so it's going to want to kind of get in that smallest surface area, which is going to be a sphere. So surface area is related to, directly proportional to, the strength of the attractive forces. The greater the attractive forces, the stronger the surface area. Okay? So we already filled in this. Okay, we talked about capillary action. I did talk to Miss Michon, the anatomy teacher, and asked about blood. Why, if you ever have to, prick your blood, check your blood sugar, get your blood typed or whatever, they stick that tube and the blood goes up because it's much more viscous. It's much thicker. It's got a more adhesive forces, so it actually travels up the capillary tube better than just pure water does. Now, so what go in those two blanks right here? Adhesive by adhesive forces and cohesive forces. All right. So, now.
Is it a CD, CO?
C, cohesive.
Oh,
The same words we had yesterday.
okay. It looks like a CD. Maybe we want to see CD.
Okay, so here is some water. Let me get another beaker. Do I have another beaker?
You don't have to see CD.
Why would it be a CD? Why would it be a CD?
Here, we're gonna sniff an alcohol.
Yeah.
So
Yeah,
bad.
I told you not to drink the alcohol.
Dude, my head hurts.
You don't
so
have no
bad.
age.
Okay.
It's illegal. Cause I was like, dang, why does this water smell like this? And I was like, nose deep.
Okay. I gotta come up here.
It was like 5 minutes. It was just no.
Okay, I have 2 beakers of water. I need a verification here though. The one on the right, kind of warm. The one on the left, kind of cool. Okay, cool, warm. Warm, cool. Gonna take one drop. Okay, can you see this?
No, you can't.
One drop of food coloring. Now, first off, why is that food coloring naturally spreading out?
Because water molecules are always
Molecules are really.
Okay, water molecules are always moving. So I think that's what you were saying as well. Okay, water molecules are always moving. Now, when do they move faster, hot or cold?
hot.
Hot. So which one's spreading out faster?
The right one.
The one on the right, is it?
Yeah.
Okay? So, but what do we call that natural spreading out because of the movement of the water molecules? It's close. It does begin with a D.
Dispersion?
It's closer dispersion, but it's not it. But you're closer in the sound. What? Diffusion. Okay? Elena gets the X.
Bonus point.
This is called diffusion. This is the result of the, what did you say, Luke?
Dispersion.
Not you, Luke.
Constant movement, I don't know.
Okay? What do you think? There's two R words that go in here.
The rapid.
Rapid,
Rotation.
random
Oh.
motions of the molecules. Okay? So, this is kind of obvious. Bigger, heavier molecules will spread out slower. If you have a big mass, you ain't going fast. Trust me, I know. If you have a big mass, you ain't going fast.
But you got more power than that.
Not necessarily. Okay? They spread out slower. Okay? Slower than smaller, lighter molecules. Now, this is all heat them up, speed them up. As the temperature increases, the molecules move faster. Move faster, Steve, because I said move. And what? What's the next blank?
And quicker.
Not random.
No, and blank, read the rest of the
Increase
sentence.
the rate and rapid.
And say what?
Increase the.
And increases the rate.
Increase the force.
Okay? Now listen, hey. Heat them up, speed them up, cool them down, slow them down. The faster, the more you increase the temperature, the faster they're going to be going. Okay? So, we heat them up. So the hot water is spreading out a little bit faster. Then there's not a big difference in temperature here. The warm water versus the cool water. The warm water, the molecules are moving faster, so the natural random motion is just going to spread out. That's diffusion. If I was to open up a bottle of perfume in here, it's just going to naturally spread out. That's what the plug-in, the Glade plug-ins for air fresheners. Okay, they're plugged into the wall, but the scent just naturally spreads out throughout the whole room. That's called diffusion. Okay, now a sister to that, as we turn the page, the sister to that is this process. Okay, everybody's seen a helium balloon, right? If I go cheap and I just buy the regular latex balloon and I fill it up with helium, what's it going to look like tomorrow?
This is gonna be less
Shriveled and nasty.
It's shriveled and nasty. That's a good way to put it. Okay, it's going to be shriveled and nasty. Why? Where did it go? It's tied really tight.
It went out
through the pores of the latex.
Okay, say that again.
It went out through the pores of the latex.
It went out through the pores of the latex. The latex has to have pores so it can
That
expand.
wasn't a shot in the dark answer. I don't know.
Hey, a blind squirrel finds the nut every once in a while. Okay, so listen. The escape of molecules through tiny openings. That's the helium finding the little tiny pores in the latex. Helium is one of the smallest, if not the smallest gas. Single atom. It's element number 2, okay? So it's got it's a tiny atom or gas molecule, they call it, a monatomic molecule. It doesn't really make sense, but it acts just as a single thing. It can fit through the tiniest opening. Whereas the bigger molecules like nitrogen and oxygen that have N2 and O2, they can't fit through those small openings as easily. I think of it as trying to go through like a doggy door. If I try to go through a doggy door, it may take me a very long time, if ever, to be able to get through the doggy door. I pray it might be for a German Shepherd or maybe a Great Dane or something. Okay? Now, on the other hand, if you take a kindergartner, they can kind of get right through. Okay? Hey, go through this door. Unlock it for me. I need to get something out of the house. Okay? And so, hey, that's the same thing as, y'all listen, that's the same thing as what's going on here. Tiny molecules can get through the smaller holes faster than the bigger molecules. So you can use a latex balloon for air for a normal balloon, but for helium you have to use mylar, which doesn't have the pores. It's still going to leak out slowly through where it's supposed to be the knot, but still it can work its way out, but it's much slower. Those good mylar balloons, if you tie a good knot, the helium will stay in there a long time. Okay? But anyone know the word for this?
Immersion.
But it does start with an E.
Inertia.
I.
He has sniffed that alcohol back there.
Oh, good.
Okay, I think I need to get that off the table back. Okay. All right, listen. Shh. Anybody? You probably have not heard of this word before.
Evaporation.
But it's a sister to diffusion. Effusion.
Sounds like some crappy.
Yeah. Smaller, lighter molecules will escape through the tiny openings faster. Okay. Yeah, it just, what's more close to diffusion? We'll call it effusion. Okay, I don't know. I'm sure there's some Latin meaning to it. All right, let's stay focused. We're struggling.
Yeah.
People all over the world are watching this. Come on, make them proud. Okay, here we go. The escape, now this is going back to basics, but this is important here. The escape of high-speed molecules from the surface of a liquid. Very good, evaporation.
Man, I feel like I should make a TikTok. My teacher's trying to get TikTok famous.
Okay, Luke, you need to stop talking. Okay? Not just for the sake of the class, but for your own sake. Okay? All right. So, evaporation. Now, here, the small technical terminology difference. The difference between evaporation and vaporization. Vaporization is the escape of a liquid even in a closed container. So the liquid in here is vaporizing and filling this space. You can kind of see the condensation around the top of the bottle here. Okay? So it's vaporizing. But when the container is open, like your beakers right there, then we call the process of vaporization evaporation. It's just the same thing, liquid to a gas, but from an open container. Okay? Now, here's the key, from the surface of a liquid only. Okay? So, I'm going to draw it. Here, we're back over here again. Okay? So I got my molecules up here on the surface just catching some rays. Now, are all of the molecules in this beaker of water going the same speed? Some are going fast, some are going slow. Why is that?
Because they're not all like the same.
They are all at the same temperature.
Because some of them have no like pushing up when it gets in the
No, but you're getting warmer. Okay, this is a graph of a liquid or a gas at a given temperature T1. Okay, now I'm going to teach you some calculus.
Oh, God.
Some non-math, some conceptual calculus. Some non-math calculus. If you want to get the area of a rectangle, it's length times width. I don't have to be on it, you just keep it on there. Okay? The area of a rectangle is length times width. You can get the area of a triangle, 1/2 base times height. Okay? You can go in any, kind of geometric shape, you have formulas to calculate the area. But when you have a curve, calculating the area is a little bit more difficult. Which is why Newton invented calculus to be able to get the area under a curve. Okay? That's the function of calculus, is you learn how to get the equation of this function here, and then you can be able to calculate the area under the curve with an infinite numbers of rectangles underneath here that then just all add together to get the area. Now, who cares about that? Well, the area under the curve represents the total number of molecules that are in my sample. That's what the area under the curve is going to be. So if I calculate that total area, that's how many molecules total I have. Well, where are the majority of the molecules? Majority of the molecules are going to be with this speed right here.
60.
Okay? However, there's some that are going slowly, some that are going more quickly. Temperature is a measure of the average kinetic energy, the average speed. It's somewhere right in the middle. But what happens is that we have the rapid random motions of our molecules. So this molecule here and this molecule gets super fast, hits this one. But just like playing pool, when this one hits this one slows down, this one speeds up. And total energy is the same. No energy is lost due to friction. Now this one goes zooming, but it bumps into another water molecule before it can go anywhere, because they're all right next to one another. Now this one goes fast and it goes flying off, but then it hits another water molecule. So they're constantly playing bumper cars, bumping into one another. But every time they bump in, one speeds up, one slows down, one speeds up, one slows down. But the collisions, we say, are perfectly elastic. There's no energy lost. So the speed, the total energy stays the same, but just some are going fast, some are going slow. But those that are just chilling here on the top, all of a sudden now a high-speed molecule hits it, bam, it goes flying off. There's nothing for it to bump into. So evaporation only occurs at the surface, because that's when they get hit by a high-speed molecule, bam, they can leave and not hit another water molecule. That's actually what happens. Now, what does that mean then? If the high-speed molecules are constantly leaving, what does that mean about the average kinetic energy, the average speed of the molecules? Okay, so if I take a test and I get the average, and then I start taking the high grades out of the average, the average is going to go down, right? So if my high-speed molecules are leaving off the surface, what's happening to my average speed? It's going down. So what's happening to the temperature of my liquid? It's going down. Why do we sweat? To cool down. Why?
Because our body has.
I know, but related to this.
Evaporation causes it to cool down.
The evaporation is the high-speed molecules leaving, so the heat from our body is being transferred into kinetic energy of the water molecules. The high-speed ones leave, the water molecules are cooling. We're taking the heat out of our bodies into those high-speed molecules evaporating from the surface. So we make things evaporate more quickly if we increase the temperature. Now if I increase the temperature to some new temperature, T2, the area under the curve, I have the same number of molecules, but I'm going to increase the range. Here's T2. T2 is greater than T1. Now what happened to my average speed? Now the majority of them are over here. We still have some slow ones, we still have some fast ones. Again, the total area under the curve, since the range expanded, the peak had to come down some because the area under the curve had to be the same because we have the same number of molecules. Okay? But the average is moving to the right. Heat them up, speed them up. So more molecules are going to be going faster. So that means more molecules hit the top with enough speed to break the hydrogen bonds holding them in, and so more molecules can escape, and it evaporates more quickly. But what about the attractive forces? If there's weaker attractive forces, like alcohol, does alcohol evaporate more quickly or more slowly than water?
Slowly. Quickly.
I'm telling you.
That was actually a G.
No, like,
Okay. Alcohol evaporates much more quickly. If you go and you put just a little bit of alcohol on your hand right there, and you're going to feel that it feels cool because it's evaporating much more quickly than the water is. Because its attractive forces are weaker. Okay? The attractive forces are weaker, holding them together so it doesn't take as much energy, so you don't have to have the super fast molecule hitting it. You can just have the medium fast molecule and it's got enough to break free. So, the escape of high-speed molecules is called evaporation. The weaker the attractive force is, the quicker, the faster the rate of escape. So then we have this term, volatile. Does anyone know what that means? If you have a volatile temper. Say that again?
Changes fast.
Changes fast, okay? If somebody's got a volatile temperature, they get quick to get mad. It goes off easily. So what does that mean about a volatile liquid? Say that again. It evaporates quickly. Very good. Okay? It evaporates quickly. Volatile liquids are liquids that evaporate quickly. A lot of people think volatile means explosive, but it just means it goes off quickly. Now let's use transitive property. I've taught you some calculus. Now let's go back to Algebra 1 or pre-algebra or wherever you learned this. The transitive property of math. A reacts with B reacts with C, therefore by transitive property, A reacts with C. Right? So, if the weaker the attractive forces between molecules, the faster the rate of escape, and volatile liquids evaporate quickly, what does that mean about the attractive forces of volatile liquids? They're weak attractive forces. It all makes sense. So if something evaporates, so perfumes. Do you want a perfume to have strong attractive forces or weak attractive forces?
Leave. You don't want it like to be able to spray it.
Okay? But at the same time, you want it to evaporate so people can smell it. If it's all on you the whole time, they're not going to smell it. But if it evaporates off of you quickly, now there's a medium there, because if it goes too quickly, then by 10 o'clock it's gone. Okay? Yeah. Okay? Yeah, everybody's smelling their pits. Yeah. Yeah. Okay? A good perfume is one that kind of is medium. Because if it evaporates too quickly, then it's kind of like a junior high boys locker room, with the Axe spray. All right? And so it just kind of smells of, that very strong odor. But at the same time, if it's too oily, then you don't really ever smell it. So you got to have something that's going to maybe be medium, long lasting. Okay? But it's all about the attractive forces. All right. So, the attractive forces are determining the surface tension, which is also going to affect the capillary action. If water wasn't as polar as it is, if it didn't have all those attractive forces, then trees would only be about 2 to 3 feet tall. Okay, we would be like that progressive commercial trying to play hide and seek in the desert, and so it's just life as we know it would be so different. But water has those unique characteristics. Thank God somehow, or thank Mother Nature, thank chance and circumstance, that we're on this third rock from the sun that happens to be the perfect temperature to where water can have this very narrow 0 to 100 degrees Celsius range that it can stay a liquid. Because we rely, and that water has these extremely strong attractive forces that give it its unique characteristics It's just amazing how that just happened. So, here's something now that you're going to get to take home with you. This is going to help you. Pressure. We're going to learn about pressure. You're going to learn that you're under pressure. Okay? This can right here, okay, come follow me on this one. This can, there's pressure inside this can. What's causing the pressure inside this can? The amount of stuff in here, but what actually causes the pressure?
There's air being pushed down onto it.
Compacted energy. But what is actually, when you blow up a balloon, why does it expand? Okay, so you're getting warmer. We'll say what? So when it's pushing out, what is it pushing out against? The latex, the balloon, the container walls. Pressure is caused by collisions of the gas molecules with the container wall. So you got a certain amount of gas inside of here, and it's bumping into the container walls. Every time it hits the wall, it's exerting a force on that wall we call pressure. Now, when I do this, are there as many gas molecules in here now? No. So what does that mean about the number of collisions? It just went down. So what does that mean about the pressure inside the can? It goes down. And so as I get more and more gas molecules come out, the pressure gets less and less and less and less until finally the pressure is the same inside and out, and the can is considered to be empty. So, pressure is caused by collisions of gas particles with, thank you, the container wall. I just said it. Seeing how well you listen. Now, let's talk about how we can change pressure. The first is to increase the concentration. This is the most obvious. You all know that you guys are learning how to drive. This is very important. If your car isn't super fancy, then you're going to have, fancy cars, you get the tire pressure gauge as reads on the dash. You can actually get the pressure of every tire. Okay? For the rest of us, you just get this little symbol on your dashboard that's an orange symbol that looks like a U with kind of a line through it. Okay? I guess you call it a trident. I'm not sure that's what it's supposed to be, but that's what it kind of looks like. That means your tire, the pressure in a tire is low. Don't just ignore that. Oh yeah, Dad, I forgot to tell you, you're going to get stranded on the road somewhere because you're getting a flat tire. Okay? So you need to get that checked. You need to get, and if some cars, it just doesn't tell you which tire. You got to go check all 4 tires. Okay? So pressure is caused by collision with the container wall. So if that light comes on, what do you have to do to increase the pressure?
Go for air.
Put more air into it. If you add more, what does that mean about the number of collisions? More collisions. More air, more collisions. So done by this can be done by adding more gas. Or, follow me over here. Okay, here's a very old bicycle pump. But how's this work? It's got a piston in here, right? And say on the bottom of this, it's supposed to be this round thing with a rubber gasket that's supposed to make a seal as it goes down. This one doesn't make much of a seal. Okay, but just imagine. So right now it's full of air. So the air in here is colliding with the inside of this tube, but it's all spread out. And so there's only so many collisions per square inch, right? But if I go and I push this down to here, now the piston's to here, all of the air that was up here is now in this small area. So the more collisions per square inch, right? Which means what about the pressure? It went up. So as I push this down, the pressure's increasing in here to where it's greater than atmospheric pressure now, and it pushes the air out and then into your tire. Okay? So by decreasing the volume, I'm in effect increasing the concentration, which in effect increases the number of collisions with the container wall. So pressure is caused by that. Now, what's the second way to do it? Second way is to blank the temperature.
Increase the
Increase the temperature. What does that do?
Make the molecules hit the walls faster.
Makes the molecules move faster,
Hit the walls with more force.
okay? And hit the container with more force and more often. Now, again, heat them up, speed them up. You heat them up, more molecules are going fast. So there are going to be more collisions with the container wall. But not only that, think about it. If a car hits a wall at 20 degrees versus a car hitting the wall at 70 degrees. 70 degrees, 70 miles per hour, 20 miles per hour. The 70 is going to be much more impactful, right? Hit with much greater force. So as you go from 20 degrees to 70 degrees, the molecules are not only just moving, they're moving faster, so when they hit the wall, they hit it more aggressively, plus they're hitting it more often. That's why if you get a speeding ticket, your insurance rates go up. Because you increase your speed, you have a better chance of having a collision. Science and the world meet once again, okay?
So if you don't get caught, then you go well.
But you're still probably gonna have the wreck, okay? So pressure is all about collisions with the container wall. We can increase the pressure either by increasing the concentration, which can be done by adding more gas, or by decreasing the volume, or we can increase the temperature, which does both. It makes more collisions and more aggressive collisions. So, what happens to the tire pressure in the wintertime?
It goes down.
It goes down because the molecules slow down, so there's less collision. So you got to check your tire pressure in the wintertime, because even though you don't have a flat, just by the temperature decreasing, the pressure is going to go down. All right, so how do we measure pressure? Okay, here, now everybody's going to want us to go to the bathroom. Okay, so here's a big test tube. It's actually called a gas collecting tube. Okay, it's just basically a big test tube. I'm going to fill it up to the tippy top with water. Again, notice how it's still wet with all the water on the inside, because water is very adhesive as well as cohesive. Okay, but have you ever noticed when you're emptying out like a glass or something and you pour all the water out and then you let it sit, then you can always pour a little bit more water out? Okay, that's because you have the adhesive forces that, you dump it out, there's a little bit of drops of water all in here, but then gravity kind of pulls them, and then the cohesive forces, the water tends to re-pool and recollect, and then you pour out that last little bit. That's again a combination of adhesive and cohesive forces. I just thought.
So what's the most like cause water is pretty adhesive and has like the high, whatever you want to call it. Well, no, like where it's like when you hit concrete. Are there any liquids that have a higher surface tension?
Mercury.
Oh yeah, because it is a liquid.
Yeah, I mean, it's very strongly attracted to itself. Okay, so now you can kind of see the dome across the top again, that surface tension, that pull. So I'm going to take and I'm going to put my thumb over it. Turn it upside down into,
And the water's
okay? And now I'm taking it off of the bottom, but the water doesn't come out. Now, is this magic or is this science? Why isn't the water coming out? Is it defying gravity?
no.
Tori's shaking her head, yes.
Like pulling it out.
Nothing. Gravity? You mean gravity all of a sudden doesn't work on the inside of here?
Yeah.
Doesn't want to let it go.
Okay. Well, we're going to talk about this thing of vacuum, but okay. So
Well, there's like a
it's a
there's a
Jack
pocket,
Sparrow
there's a
thing.
pocket of
Is it
air
blue?
in between the water and the little beaker. And
No. if there was air, it would come out if I kind of turned it sideways.
No air can get
Okay, Connor, go ahead.
There's water that's in there, so it can't, like, in order for the water to leave, there has to be something that goes up in there, like air. And there's no
That's not necessarily true. You could have a vacuum up here.
Doesn't want to suck up the vacuum that low pressure.
Those
Okay?
are vacuum.
Let me ask you this. Okay? If this water comes out, what has to happen to the water in the beaker? Has to go up. So gravity wants this water to come out. Something is resisting it. Something is resisting this water level from coming up. No. That's a good guess.
Water molecules are like pushing like into it.
No. Well, in a sense they are, but something has to be applying that force.
Water pressure?
Not water pressure.
Air pressure? Does gravity not let the water go up?
Gravity only goes down. Gravity only goes down. So what did you say?
The
Air pressure.
The air pushing down on the water, it doesn't.
Right now, we have about 50 to 100 miles of air above us. We don't think about it. We walk through it every day. But the reality is that we are always under pressure. This is probably not a new revelation to some of you. You always feel the pressure. So here, this is full of water. In order for the water to come out, this level has to go up. So something is resisting that. And that something is the atmosphere.
The ATM, the bank.
Right now, if this is pushing down with a certain amount of force, trying to make this come up with a certain amount of force, the atmosphere is winning the push of war. The atmosphere weighs more than the water.
So wait, so if we were in like a vacuum, that water would come out?
If we were in a vacuum, that water would come out. Okay? But now, does anybody scuba dive? Have you? Yeah. I want to. It's a bucket list, and hopefully in the next year or two, I will get certified. I'm going to scuba dive in the Caribbean or somewhere in one of the saints. Okay. I probably won't go back to Costa Rica since I've already been there, but
Did you not like it?
I did like it, but
Oh,
I want to just see other places. Okay, I don't limited time left. So, you got-
Bora Bora.
well, I thought about going to Bora Bora at one point. Okay, now listen. When you scuba dive, does anybody know how deep do you have to go to double the pressure on your body?
20 meters.
How deep under the water do you go? Because you know how your ears start to hurt when you go under the water?
200.
How far do you have to go to where you double atmospheric pressure?
Double your height.
20 feet.
8.
You're close, but a little bit more.
What do you say?
12.
He said 20.
I thought it.
Okay, it's
30?
between 33 and 34 feet.
33 and a half.
So if I went and got a 35-foot test tube, filled it up to the tippy top with water, that's about from the middle of this window to the ground. Okay, so I have a beaker of water on the ground. I get a big old test tube, fill it completely full of water, put my thumb over it, turn it upside down. Somewhere between 33 and 34 feet, the water is going to come to a rest. Because then the weight of the water is going to equal the weight of the atmosphere above me. Okay? Now, when a high pressure system would come through, it would push more on the surface of the water. What's that going to do to the water level inside my tube? It's going to go back up. Now, by the way, what's above? If this drops down, what's going to be up above here? Where's air going to come from?
Nowhere. It's just gonna be.
Nowhere. That's what we think is there because it's just natural. If there's a gap, we think it's air. But it's really going to be a vacuum. There might be a little bit of evaporated water, but pretty much a vacuum. Okay? So we can have a vacuum above it. It's just that the weight of the water pushing down is equal to the atmospheric pressure. Now, when a storm comes through, like it's supposed to on Friday, then a low pressure, so it doesn't push down as much, what's going to happen to my water level? My water level. It's going to drop. So I've created a barometer, be able to measure atmospheric pressure by how tall of a column of water the atmosphere can support. Okay? But a 34-foot barometer is not very practical. So instead, they decide to use the one liquid metal, mercury, which is 13.55 times more dense than water. So what takes 33 to 34 feet of water only takes 760 millimeters of mercury. 760 millimeters of mercury 760, is right here. Oh, right. Yeah.
Close up.
So my column of mercury only has to be this tall. So now you're going to have to give it some room to grow, so they probably make it about this tall. Okay? So the guy at the mercury factory gets a tube just like this one, fills it full of mercury, puts his thumb over it, and turns it into a small bowl of mercury. So now we're supporting a column of mercury. So we say that 1 atmosphere of pressure, normal atmospheric pressure, can support a column of mercury approximately 760 millimeters high. But that changes every day. This is just what we call normal or standard atmospheric pressure. This atmospheric pressure changes every day. High pressure system comes through, it goes up. Low pressure system comes through, it goes down. You go up into the mountains, there's less air above you, the pressure is less. You go down to Death Valley in California, the lowest point in the United States, there's more air above you, the pressure is greater. Okay? It varies on sea level. How far above sea level are you? The normal atmospheric pressure changes. But we just say standard atmospheric pressure. And by the way, 1 atmosphere is an actual unit of pressure as well, an atmosphere. And we're going to use it a lot. 760 millimeters. Now, a guy named Torricelli invented the first barometer. So this millimeters of mercury got named after him. So it's exactly the same. A millimeter of mercury and a torr are exactly the same thing. It's just named after him. Millimeter of mercury is the actual measurement. Torr is just in his honor. Now, we're in America. America. We can't do anything the rest of the world does, so we have to do ours in English, in the English system, in inches. So 760 millimeters, when I go here 760 millimeters, I turn that over and it's 29.92 inches. .92 inches. So when you watch the weather and you see James Spann, he's talking about the barometric pressure reading, he's going to give it to you in inches. Anything over 29.92 is a high pressure. Anything less than 29.92 would be considered a low pressure. Now when you have a hurricane coming through and that thing's spinning, the faster it's spinning and the bigger the hurricane, the lower that pressure is going to be on the inside. Because it's kind of just it just swirls, it creates a suction inside of it. It lowers that. Now, more practically, it's 14.7 pounds per square inch. That's how we measure it here in America, PSI. So whenever you see PSI, that's pounds per square inch, which the metric is 101.3 kPAs. Now, any y'all ever seen the little tire gauge where you put it on the stem, the tire, you push down on it, pops the thing out the end? Okay, you have to measure your car tire, bike tires. You push it down, pops it out, and you get the pressure. One side is in black and one side it's in red. The black measures it in PSI for us here in America. Car tires should be about 32 to 35 PSI. Okay? But the rest of the world uses KPA, kilopascals. That's the actual metric. This is the metric unit, the SI unit, right here. Okay, 101.3. But what does that mean? Okay, you're gonna have to. What is this? What do we call it? Suction cup. So what is suction really? Okay. I push this down on the table and I pull this up. Well, I push this down and then I pull this up. I've created suction now to where I can lift the whole table. Okay? These tables are heavy. So what is suction? Why is this stuck to the table so hard?
The air can't escape. The air can't escape. It's stuck to the table. 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 It's stuck
The air can't escape, so why does that make it stick so hard?
Is it pulling the cable? It's like convective.
It has a very low pressure on the inside, so
Okay, so it's got low pressure on the inside, big whoop. Why can't, I'm trying to pull it up
it's being pushed down to the table.
by, it's being pushed down onto the table by the atmosphere, which weighs 14.7 pounds for every square inch. So if I go and measure my square inches of this suction cup, you can see that it's probably between 10 to 15 square inches. Okay? So 140 to 200 pounds of air pushing down on the surface of this suction cup. So when you go and you want to hang a picture on a window and you have the little suction cup and you lick it and you stick it on there, you call it suction, but the reality is you lick it to get a good seal so no air can get in. So then you have an unbalanced force of just the atmosphere pushing in, and the atmosphere pushes in all directions because the air is moving in every direction, 14.7 pounds per square inch. So if you have like a 1 square inch little suction cup, it's going to be able to hold, almost 14 pounds. Now you probably don't have a complete perfect suction in there, but you're going to be close. Yeah, so all I'm doing here when I open this up now is that lets air in, and so now I can just lift it right up because now I'm pushing up with 14.7 just like I'm pushing down with 14.7. So now I just have to overcome gravity. So suction really isn't suction. Suction is imbalanced force, and it uses the atmospheric pressure to push down to keep me from lifting it up or being able to remove it. Now, I have the coolest one in my bathroom. In my shower, I have a shelf. Okay, normally when you have the suction cup shelves, like to hold soap or something, they start falling off all the time. Okay, because air gets in back behind them. But this one, you can actually screw in and tighten it down and get a really good suction on it, because it's just like this, you're just really just pushing all of the air out and making a perfect seal and pulling that thing super tight against the wall. I've never seen one like this before, but that thing never falls down, and it's wonderful. Okay, and we got all kinds of stuff weighing on it. Okay.
Get myself one of those.
Yeah, I mean, my wife got it. I don't even know where she bought it from, but you just screw it in, and it's really quite ingenious. I wish I had invented it. So, okay, so these are different ways of measuring pressure. So we're under this pressure all the time. Now we need to be under this pressure. Have y'all ever seen the sci-fi movies where they go out in space and somebody gets thrown out of the spaceship? What happens? They die. Okay? Well, it's not, the cold would kill them too, because it's super cold. It's almost like absolute zero in space.
Oh.
Unless you're in the sun, then it's like 400 degrees.
Yeah.
But what happens is that your blood vessels, as your heart beats, they expand and contract, expand and contract, expand and contract. Well, the atmosphere is helping to control that, keeping them from expanding too much. Like a balloon, if it expands too much, it bursts. So the atmosphere is pushing down, so it resists it from expanding. Okay? Now, y'all have heard of nosebleed section, right?
Yep.
Those are the ones that are super high up. Because if you go skiing in the mountains, where the atmospheric pressure is way less, you have the little tiny capillaries in your nose. Those are the most sensitive and the most exposed capillaries. That's why you snort cocaine. Well, not you guys, but that's why people snort cocaine, because it can get absorbed into those itty bitty tiny little capillaries in your nose. No, I am not at all.
That's why we use
Okay? Now listen, those capillaries then are very exposed and very tiny. So when you go up into the mountains, there's less pressure holding them, pushing in on those. So when your heart beats, they expand and then they tend to break. And you get nosebleeds in high altitudes. because there's less pressure. So they're saying at a football stadium, you're so high up, the altitude is so you know, the atmospheric pressure is so low that you're going to tend to get nosebleeds because there's not as much holding, helping your nose to keep from, you know, the blood vessels from bursting as your heart beats. Okay, especially if you're walking up the stairs and you get your heart rate really up high, you know, and your blood vessels going, you know. So when you go skiing, a lot of people get bloody noses when they ski because increased heart rate and then the lower altitude, the higher altitude, lower atmospheric pressure. Okay? So, what did we say is the instrument used to measure atmospheric pressure? A barometer. Okay, so a manometer, though, is used to measure vapor pressure. And again, I'm opening up this thing called a book.
Where's the on button?
Okay. Okay, so here's just a kind of a picture, just like I just showed you, though, of a barometer. A glass tube full of mercury. It is indeed a vacuum above there. There's nothing pushing down. Okay, so you fill the mercury all the way up, but it drops down to here. So the weight of this mercury is the same as the weight of the atmosphere pushing down. I've tried hard to find a picture of an actual mercury barometer, but I can't find one. But so that measures atmospheric pressure. But a manometer is this, and it's the original U-tube. It's a U-tube of mercury.
YouTube.
Oh, that's so cool.
Doesn't make sense. Why?
Okay, so before I do anything, if I fill this up with mercury, gravity is just going to pull it equally on both sides. This is a vacuum up in here. Okay? So there's nothing pushing down on this side, so it's just gravity, and this is mercury inside my tube. This is a manometer. Now, let's just say we put some ethanol in here, some C2H5OH. That's the same stuff that's in front of you right now. Okay? Now, could you smell it when you put your nose over it?
Yeah.
Why could you smell it?
Because of like the thing that's been there, so you're both.
I know, but no. It's evaporating. If it was all a liquid,
What does water smell like?
it doesn't have an odor, but it's still evaporating. Okay?
Doesn't gas have no smell, but they like put like the smell?
Well, gasoline is a mixture of 40 different things. Natural gas doesn't smell. So they put the mercaptane, which is a very foul-smelling sulfur compound, so you can tell when there's a leak. Okay? So, this ethanol is going to begin to evaporate. And so you're going to get gas molecules all up in here. Now you open up the valve, and it goes down here. So it's going to then push down on this side of the mercury. Well, there's nothing on this side. It's a vacuum. So what's going to happen to the mercury?
Fill up that like,
It's going to move up. So the mercury now is going to go and fill this. So the difference between here and here is a certain number of millimeters of mercury. So we say the vapor pressure of the alcohol is this many millimeters of mercury because it's supporting a column of mercury that tall. Now again, the vapor pressure. Who remembers the definition of a vapor?
it's like something water.
something water. Close. It's not anything in the gas state because we have oxygen gas, carbon dioxide gas, nitrogen gas.
Water inject, so liquid molecule.
So what are you saying, James?
I was gonna say, with possible liquid in the gas state, something that's
Okay, something that's normally a solid or a liquid that's in the gaseous state. Water vapor, alcohol vapor, gasoline vapor, Vicks vapor rub. Okay? So, right now, if I leave this bottle and it's screwed on tight, will the water level in here go down?
No.
Yes, Dr. Pepper.
Well, I drank the Dr. Pepper, now I just fill it up with water. Okay? So if I just leave this, the water level, is water evaporating?
No.
Vapor, is it vaporizing?
Yes.
Okay? But why doesn't it all go down then?
Because it's not going anywhere, the what vaporized, they just pound it.
Why doesn't the whole thing become vapor then?
It just takes time.
So if I came back in 100 years, this whole bottle would just be vapor?
Yeah.
Because it doesn't like the vapor like condense again and it's just in the cycle of it.
Okay? Because once there's so many water vapor molecules up here, then they start colliding with one another and going back down, and we call liquid to a gas. What's this change of state called? Condensation. Okay? So it's vaporizing, but then once it gets so full, it begins condensing again. Now, the stronger the attractive forces are, the more they're going to just kind of bump into one another, stick together, and go back down. But if they're weak attractive forces, hey, I don't like you, you don't like me, they just bounce off one another and they stay in the vapor. So the vapor pressure is the pressure exerted by the vapor above the liquid. Okay? The vapor pressure is the pressure exerted by the vapor above the liquid. If something has a weak attractive forces, if they have weak attractive forces, it's going to evaporate quickly. We'll have a lot of vapor. So what does that mean about collisions with the container wall? If you have a lot of vapor, a lot of collisions, so you're going to have a higher vapor pressure. So if I have alcohol in here, I'm going to have it evaporating pretty quickly. But if I change this to water, I'm not going to have nearly as many vapor molecules. And so as a result, my vapor pressure is going to be less. I'm not going to be able to push down as much. But a manometer is able to measure the vapor pressure. We can put it in here and measure the pressure exerted by any gas. How much, you have the liquid in here, and then you just check and measure how much pressure is that gas exerted, measured with a manometer. Okay? So this is in your book on page 351. Page 351.
No. It's one of the books.
So, I'm going here now. Manometer is used to measure liquid's vapor pressure. So, by definition, then the pressure exerted by a vapor above its liquid, it's called vapor pressure. Okay, I'm not going to write these in, so you just pay attention. So what would we say? Liquids that have a high vapor pressure have weak attractive forces. Low vapor pressure, strong attractive forces. Okay? So, but if we increase the temperature, what's that going to do to my rate of evaporation? If I increase the temperature on this water,
It increases the rate of evaporation.
so there's going to be more vapor, right? What does that mean about vapor pressure?
It's going to be higher.
It's going to be higher. So once again, in your book, I should have closed it. It was on the very next page. So when we look at this graph is very important. Okay? Come on, hang with me. I gotta finish this. I gotta finish all these blanks by the end of the period. Okay?
You have 7.
I'm aware of that. So I need everybody. Here we go. Because this is the most important thing. So as I'm increasing the temperature, more water molecules, more anything is going to evaporate more, which means you're going to have more vapor molecules, which means you're going to have more vapor pressure. So you can see here that as you're increasing this, but what can we say, diethyl ether versus ethanol, which is what's in your beaker, versus water, which has the strongest attractive forces?
Water.
Why?
It has the highest boiling point.
Highest boiling point, but what about a vapor pressure?
It's the highest.
At any given temperature, at 40 degrees, what's the vapor pressure of water?
Not very high.
Not very high. But ethanols is even higher, and then at 40, it's not even on the graph. So if I went to 20, it's here, here, then here. So diethyl ether has the highest vapor pressure at any given temperature, which means there's the most vapor molecules, which means it's evaporating the quickest. Okay? So the higher the vapor pressure, the weaker the attractive forces. So if you want to recreate this diagram, diethyl ether is going to have the weakest attractive forces. Water is going to have the greatest attractive force. Now, what's unique about this boiling point being 100 degrees?
It's the same as when it hits like that little line.
With that little line, which is, where do you think the pressure is?
It's that's like the air pressure.
That's normal atmospheric pressure. So we define boiling. Boiling occurs when the vapor pressure of a liquid is equal to atmospheric pressure. Going to come back to another one of my exciting drawings here.
You said atmospheric pressure?
Atmospheric pressure. So once again, we have all of our water molecules down here, and they all just want to be free. Because the gas, they're random, they're free. They get to do whatever they want to do, go wherever they want to go. They're not attached to anything. So, we talked about what's in the bubble when water boils.
Air.
Water, right? Because we're breaking those weak hydrogen bonds. But if I form a bubble and this goes out here, this goes out here, this goes out here, here, and here, what's going to happen to this water level right there? If I make a bubble here, it's got to go up, right? What's keeping it from going up? Atmospheric pressure is pushing down. So it's not until the outward push, the vapor pressure of the water, is equal to the downward push of the atmosphere. When those two equal, that's when the bubble forms and we can get boiling. Boiling is when that vapor pressure, the outward push of the water molecules, equals the downward push of the atmosphere. So if a high pressure weather system, if you push down harder, what does that mean? We have to make the vapor pressure higher. So let's go back to that graph. Oops, keep this down. Quit closing the book. So again, if I'm looking at this, this is my normal atmospheric pressure. But if a high pressure system comes in, that means that the pressure of the atmosphere is moving up. I'm going to have to increase the temperature to make it boil. But if I decrease the pressure, I can make water boil at a lower temperature. Will you stick your finger in that for me, please? Is that hot or cold? Okay, is it burning your finger or anything? I think this was water. I don't think it was the acid I hit in there. No, I'm just kidding. It's water. 100%.
Ash doesn't trust you.
She's not trusting me at all. Okay, so this right here is a vacuum pump. This thing really sucks, okay? Okay. So now I'm sucking all the air out. So basically what I'm doing is I'm pulling and lowering the atmospheric pressure. Boiling occurs when the atmospheric pressure equals the vapor pressure. I'm not changing the temperature of the water at all, I'm just lowering the pressure. Why do I have to use fresh water?
Why do you do it like that?
Because it's supposed to be boiling already. There we go.
It's very strong.
Well, it's going to speed up. It should. These are new vacuum pumps, and I don't think they're as good. Well, we're right on the edge. All right, hold on. For some reason or other, if I use fresh water, it works better.
I didn't break it down. It's like open a spaceship.
Well, I'm gonna make it water just because I'm cheating, but
Did you ethanol and it'll boil even quicker?
yeah, that's true.
But then you blow up in your face.
No,
Why do you think it's gonna blow up? It's just boiling.
Yes, you put light in it.
That would be.
You'd be like moonshiners.
okay, let's try this again. So I'm sucking the air out.
There it is.
Okay, so now the water is beginning to boil. I haven't heated the water up at all. I am just lowering the atmospheric pressure to where vapor pressure, way down here, vapor pressure is equal to atmospheric pressure. So the pressure inside has come down all the way down to here. Okay? And now it's boiling. And generally it can even boil more vigorously, but we have a leak somewhere. It's not getting good. Okay, but if you can't see it, it's definitely boiling. I'm going to try it with ethanol. I've never done it with ethanol.
Should I stop the video saying what?
Where's the ethanol? Pass me the ethanol. Just try it. I don't got my bag. So why is the water running for the alcohol? What kind of defeats that? Yeah. No, there's vacuum space.
That's really bad.
Well, there's a leak somewhere. I'm surprised that alcohol isn't boiling at all.
Well, it has other stuff.
Well, it still has a much lower boiling point than water, so it should be boiling soon as the pressure.
Yeah, it should be people boiling.
Science lies to us.
Your science is failing right
You
now.
can't trust your science.
Your science is failing. The video's failing.
once we get down here, I mean, the second boiling point isn't very much different, but still, I think we're gonna get the other vacuum pump. Disappointing.
Want me to stop the video?
Yeah.
Alright.